This will be a quick, easy lecture on beam restriction. Okay, looking here, you have some objectives. Make sure you're able to identify, discuss, and explain these different objectives so that you understand the material very well. Let's first talk about our KVP. So we're looking at Compton scatter. That's the reason why we're collimating. That's the reason why we're having these lectures on KVP, scatter, beam restriction. Everything is because of this Compton scatter, okay? So remember, it's an interaction, right? So the Compton scatter provides no diagnostic value to our images. And the main way that we get Compton and the way that we can control is with our KVP, okay? So if we look at KVP, it affects the penetrability of the beam. So we talked about that. That is our energy of the beam. It is the energy required to penetrate a part. And as you remember, we have to have transmission of the beam through the patient, right? We have to have photoelectric absorption, right? So we get the black and white. Now, as a side effect in that, we also get Compton scattering. Compton scattering degrades our image, right? So it provides shades of gray that are not true representation of the actual radiated material, right? So when we take a look at KVP, we're also going to look at the volume of irradiated material. We're going to look at the field size and the patient thickness also. How do they play a role, and what are we doing with our KVP, and how is Compton scatter affected by all of this, okay? So, effects on interaction. So if we take our KVP and we increase our KVP, what are we doing? We're increasing the transmission through the patient. So when we do that, naturally, we're decreasing the photoelectric absorption. And if we increase our KVP, we're also increasing our Compton scatter, which is bad. But if we're decreasing our photoelectric absorption, which is 100% patient dose, that's a good thing. So there's a compromise here. So what are we going to do to help control some of this Compton scatter that we have to deal with, as it's a product of the KVP? So, effect on patient dose. So if we increase our KVP, we're decreasing our dose because we're decreasing the photoelectric absorption. So remember, the photoelectric absorption is 100% dose. All of that is being absorbed in the patient. So if we increase our KVP, we're increasing our transmission, which is decreasing our photoelectric absorption. So and normally when we do increase our KVP, we're reducing our mass. So we are reducing our photoelectric absorption by decreasing our mass. So effects on image quality. With digital imaging, it's not as predominant. It's not as pronounced. So we are able to use post-processing to help clean up some of our Compton interactions, okay? If we decrease our KVP, we're decreasing the transmission, which means we are increasing our photoelectric absorption. We are also decreasing our Compton scatter. So what's happening here is we're increasing the patient dose, but we're decreasing our Compton. So where are we at, and what are we trying to do? We're trying to find the happy medium, okay? So if we decrease our KVP, we increase the patient dose by increasing the photoelectric absorption. Decreasing KVP usually is accompanied by an increase in mass. So if we decrease our KVP, we need to kick up our mass, all right? We set the KVP based on the body part, okay? So if we increase our mass, naturally we're increasing our patient dose. So the effect on image quality, once again, it's not as noticeable due to post-processing, okay? So we can play with our KVP and our mass and not see the effects like we would when we used film back in the old days. All right, so let's take a look at the volume of irradiated material. So we're going to look at our field size, and I'm going to use the abbreviation FS, our patient thickness, and our average tissue density. So if we look at field size, increasing the field size increases the volume of tissue radiated, okay? So that means you're making your collimation bigger, right? If you decrease the field size, then you're making it smaller, okay? So if you decrease your field size, you're decreasing the amount of scatter radiation. you're decreasing the amount of remnant radiation hitting the image receptor, and it can increase the noise. So remember, we talked about noise. Noise, quantum model, quantum means number, right? And model is noise. So if we take the quantum model, if we decrease our field size, we're reducing the number of photons by using our lead collimating shields, right? So they're blocking photons from hitting the image receptor. So if we're going to collimate really tight, we're going to decrease our collimation. We need to increase our mass. Okay, now that doesn't necessarily mean that the patient's getting more dose, because we're blocking those photons from making it out of the collimator box with our collimation. Okay, so you've got to kick up your mass if you're going to decrease your field size. Okay. Trade-off: by decreasing your field size, fewer photons reach the image receptor. So the image receptor exposure is decreased. So you're going to get that salt and pepper look where we're missing photons on our image receptor. So increases in mass must accompany significant reduction in field size to maintain the IR exposure. Okay, so you've got to make sure that if you're collimating really, really tight, if you're decreasing your collimation, that you are able to kick up your mass to compensate for those photons that are being absorbed by the lead shutters. Okay. So patient thickness. So thicker body parts produce more scatter. Well, that makes sense. Denser body parts produce more scatter. Yep. So the thicker it is, or the more compact the atoms are within the body, more scatter is going to be produced. So both these factors increase the number of interactions X-ray beam undergoes as it passes through the body. Makes sense. So patient thickness, denser body parts produce more scatter, so higher electron. If you don't like electron, because electron's kind of weird for me too, I say atoms, okay? So higher atom density presented in thicker or denser body tissues. So they're in there, it's either thicker, so taller, or it's more compact, okay? So with that, we're gonna have more photoelectric absorption. So the photons are gonna be absorbed within the body, okay, rather than making it out of the patient. So decreasing the part thickness. So what you want to do, if you have a patient that is 600 pounds, what we do is we use compression devices so that we can improve our spatial resolution and contrast. So decreasing part thickness, thickness becomes more uniform, okay, and it lowers the patient dose, and it brings the tissue closer to the image receptor. So we do this by decreasing the OID. And when we do that, as we have learned, it increases our spatial resolution. Win-win. We use this general concept in mammography. So we compress the breast tissue to make it more uniform, okay, improve spatial resolution, and get all the tissue closer to the image receptor. So we also do it with large patients. We'll take compression devices and compress the abdomen so that we can get a better detailed or higher spatial resolution image. Okay, control of scatter using beam restriction devices. Ideally, beam restriction decreases field size to anatomy of interest. So isn't that a win? So number one thing that you can do to control scatter is collimate. So what do we do here? It's unnecessary tissues are exposed. Yay. Scatter is decreased. Yay. Scale of contrast shortens. Now, when we talk about scale of contrast, remember we talk about short scale, long scale? So this shortens. So we have black and white, not a bunch of shades of gray like we do from the scatter. Okay. So we want a shorter scale of contrast. And our visibility of detail increases. So all of these are great things. These are all good. So number one thing you can do, collimate, collimate, collimate. So there's different beam restriction devices. So there's aperture diaphragms, there's cones, and there's cylinders, and we talked about that in our last lecture. So the principal disadvantage of these is it's a fixed field size. You can't collimate, okay? So with cones and cylinders, we don't use them very often. Aperture diaphragms, fixed. We like variable collimators, right? And we're going to talk about some ancillary devices also. So we don't normally use these cones or cylinders anymore. Very common way back in the dark ages when I first started, but nowadays not as common, okay? How's going to a collimator? This is what we're using in today's world. We have these collimators. They're variable, so we can adjust the sizes, right? and it has a light that's representing the exposure field. So it has a light that comes out of the collimator box that matches the X-ray field size. Okay, provides indication of midpoint of central ray. There's 2 sets of shutters that permit infinite number of sizes, so the length and the width of the field, independently controlled, permits reticular collimation. Yes, so yeah, you can collimate either way, okay? So infinite number. Now, the really important thing is to understand and realize that we're using lead. So the X-rays cannot penetrate the lead shutters, okay? So when we collimate, that beam coming out off the anode is still the same size. And what we're doing is we're shaving off, the lead is absorbing all those photons that normally would be there. We're blocking them, okay? So only a few of the photons are making it out of the collimator box between the lead shutters. So it's absorbing your photons, so you need to kick up your mass, okay? It's not necessarily meaning that the patient's getting more exposure, okay? It just means that those lead shutters have absorbed a lot of your photons if you're collimating really tight, so you need to go to a higher mass just to compensate for those lead shutters absorbing your photons. All right, so let's talk about the collimator and penumbra. Now this is interesting information here. So the bottom shutters reduce penumbra. So we talked about penumbra as the area of unsharpness, right? Geometric unsharpness around the periphery of an image, also called edge unsharpness. So it improves sharpness of the recorded image. So that's really good. So you do want to collimate because it helps reduce your penumbra. So if we look at collimator and off-focus radiation, so we have off-focus radiation, there's nothing we can do about it. So when you take an image and you see the ghosting outside of your collimated field, you can see some exposure, that is your off-focus radiation, okay? So off-focus radiation occurs from areas of the X-ray tube other than the focal spot. So the electron is hitting on the anode in any other place other than the focal spot or focal track. Okay, so it's being produced outside of the focal spot, focal track. So the upper shutters reduce off-focus radiation from reaching the IR. So the tighter you collimate, the less off-focus radiation that's going to be exposing the patient, which is a good thing, okay? So off-focus radiation produces images beyond the exposed field, so it's those shadows that you see. So your light field uses the light reflected off a mirror to project coverage of the X-ray beam. So proper adjustment of the mirror is necessary to accurately display the location of your exposure field. So the light field / X-ray beam coincide testing should be part of the quality control program. So this actually has to be tested. It needs to be accurate within plus or minus 2% of your SID. So the mirror also adds inherent filtration, and we've covered that already. So if you think your light field, X-ray field is off by a little bit, you can just put a paper clip on the corners and where the light field is showing on an IR, and then make an exposure, and you can see how far off it is, and you can calculate, and it can be plus or minus 2%. And let me tell you, it's quite a bit. To be legal, you can be off by quite a bit. So you just have to know your machine. Like you'll be like, Christy, you know, I'm looking at your comps. You're like, oh, but the light field, X-ray field was off. I go, it's your job to know which way it's off. So you need to be able to compensate. Sometimes it's like half an inch. So, and it's still within code. So you have to know, okay, it's off to the right by half an inch. So don't clip your fingers off or your toes or clip your knees or whatever because your light field, X-ray field is off. But please pay attention and just put those paper clips in the corners and make an exposure, and you'll be able to see which way it's off and how much it's off so you don't clip your fingers. All right, so features of collimator housing. So central ray must be marked. So some units project location of AAC sensors on the light field. So sometimes it'll show you where your AACs are, which is kind of nice. Alignment helps Alignment light helps center the beam with the image receptor, of course. Newer systems will automatically adjust the field size in changing with SID. So we call that PBL, positive beam limitation. So automatically collimation of the beam to the size of the image receptor, which is really nice. You can override it. You can make it smaller, not bigger. Okay, and is no longer a federal requirement. Used to be, still very popular among technologists. I still like using it because I turn the key on and it opens up to my IR size, which is kind of nice, and then I just collimate in from there, so I'm sure I'm not exposing larger than my IR. All right, so ancillary devices, lead blockers. Kind of nice. Shields, we have those. We have both those in our classroom. Lead masks. These are interesting. They attach the columnar head. We used to use them all the time for scoliosis to protect the breasts and the ovaries or the testes on a male. So it's vendor specific. So it's kind of, it depends on, the maker if they have these or not. Okay, so that's your lecture. I told you it's quick and easy. If you have any questions, please be sure to email me.